Welcome to Module 2 and Finite Automata. In this video, we're going to talk about deterministic finite acceptors, or DFA for short. All right, so first let's remember what an automaton is. An automaton is an abstract model of a digital computer. It takes input, which is a string over a given alphabet. It reads input from left to right, one symbol at a time. So if you need to be familiar with what an alphabet is, a string is, and symbols of an alphabet and all of that. You can represent an automaton, which is singular for automata. It can be represented by using a graph. So we are going to use a graph to do our automaton, and we're going to start by doing acceptors, and we're going to test and see different types of languages. So we're going to use a graph to do that, and the graph will have vertices and directed edges. So this right here shows that you can move from state 1 with an A into state 2. So this is how you read how these graphs work. All right, so now let's look at an acceptor that accepts legal C identifiers. What does that mean? The programming language C. So if we were going to have a string, and we were going to feed strings into this acceptor and see if it accepts strings that are identifiers that are legal in the language C. So we start out with an initial state. We would have an initial state, and then we would feed symbols from our alphabet into it. So if we were to give our first symbol, let's start from left to right. So if our first symbol is a letter or an underscore, that would be accepting, because that means that any identifier in the language C can begin with a letter or an underscore. But if the first symbol in our string that we're entering into this automaton or acceptor were a digit, then we would go to a non-accepting state. So an accepting state is just a state that has a double circle on it for these exercises. So you can see here, if we take any string and it begins with the letter or an underscore, then that would be accepting. If the string begins with a digit, then that would be not accepting. And then if we continue, as long as we begin with a letter and underscore, and we continue to have letter, underscores, or even digits, it doesn't matter. As long as the first character or the first symbol of the string were a letter or an underscore, then it would be an accepting legal identifier in the language C. So this is the kind of graphs that we're going to be using for DFAs. All right, so the difference between an acceptor and a transducer is just that an acceptor is going to accept with yes or no, like have an accepting state, where a transducer capability is to produce output. So the automaton that we're going to be working with, the DFAs in this video and the NFAs for this module, are all going to be acceptors. They're either going to lead to an accepting state, or they're not going to accept the string. So basically the way it works is you just run the symbols through the machine or automaton, and if you get to the last symbol in your string and you land in an accepting state, then it would be accepted by that language, and if not, if you land in a not accepting state, then it would not be accepted. All right. So this is just some differences again about a transducer versus an acceptor. They both have a finite number of states. They both process an input string, in other words, a sequence of symbols. They both make transitions from one state to another. So again, you process the strings from left to right, and they both produce some output. But where an acceptor, the output is just going to be accepting or not accepting, a transducer actually will produce output. All right, so now let's talk about what a DFA is. A DFA is called a deterministic finite acceptor. It has a finite number of states, and it is deterministic, and it is an acceptor. And the formal definition of a DFA is a 5-tuple. If you notice up there, when we were doing grammars, we were defining our grammars with a 4-tuple. A DFA is defined with a 5-tuple. So let's talk about what's in this 5-tuple. The first, the Q, stands for a finite set of states. So that is the set of the states of the DFA. The sigma is the finite set of symbols, which is called the input alphabet. This is the transition function. The transition function, you go to the state and then you process the alphabet symbol, and then you move to another state. So you start in one of the finite states, you process a symbol, and then you will move to another state. You might not move to a separate state, you might stay in the state you're in, but that's a transition. You transition from one state to another, or you can transition and stay in the same state that you're in. Q0 is the initial state. So before we had 1 was the initial state. Now we have Q0 as the initial state. We'll number the states with Q0, Q1, Q2. It doesn't really matter. That's just the convention that we'll be using. And F stands for the set of final states, or the set of final states are also a subset of all of the states. All right, so let's do some examples. A string would be accepted if, after consuming each symbol, the DFA ends in a final or accepting state, which is a state with the double ring. All right, so here's an example. We have a DFA and our alphabet is AB, and our language is going to be all strings with no more than 3 A's. So if you can create, so this is where you would do a proof by construction. If you could create a DFA that accepts all strings with no more than 3 A's, then that means that that would be a regular language. Now, we haven't really talked about regular languages yet. We're just getting, we're getting started with how to use these automatons. So, but that's what we're working up to. DFAs and NFAs are the acceptors for regular languages. All right, so let's the most basic languages that we're starting with, if you remember from the hierarchy of languages. All right, so let's create a DFA that the alphabet is A and B, and it will accept all strings that have no more than 3 A's. So how do you construct the DFA? All right, this is what the DFA looks like, and these are the transition functions, and now we're going to construct it one by one, each state one by one. All right, so we start out with our initial state, which is Q0. Now Q0 is a double ring around the circle because it is an accepting state. If you have a language in which all strings with no more than 3 A's is accepted, that means that a language with no A's would be accepted, right? So this is the transition function now. If we are in Q0 and we process an A of our string, we will move into Q1. So a string with 1 A is also accepting, is also part of the language, right? If you have just the string A, if you have the empty string, which has no A's in it, that's accepting. If you have a single A, that is still a string with no more than 3 A's. So that's a transition function now from Q1 with another A is going to lead into Q2. This would be the string AA. That would also be accepting because it has less than 3 A's. And the next transition from Q2 with an A would go into Q3. And again, the string AAA is a string with no more than 3 A's. Now, I haven't done anything with the B's yet. All I'm doing now is building my DFA. And so I'm building it step by step and talking to you about it while I do that. So we can tell by looking at this that the empty string, the string A, the string AA, and also the string AAA are all accepting. But what if I have another A? Well, if I have another A, I'm going to go into, it is not going to be accepting because that means I now have a string with 4 A's. So A is a string with 4 A's, and that is going to lead to a non-accepting state. All right, so now we just have to deal with the B's, right? Oh, no, we have to deal with any more A's. So after I have 3 A's and then I get my 4th A, it's not accepting. I get my 5th A, 6th A, 7th A. If I get any more A's, it's still not accepting, and it will never go back and be accepting. Now, what about B's? All right, well, what if I'm in Q0 and I get a B? I'm going to stay in Q0 because I can get all the B's I want, and it's accepting. A string of 1 B is accepting. A string of 100 B's is accepting because a string with 100 B's has no more than 3 A's, right? So what if I get 100 B's and then I get an A? Still accepting. But what if I get 100 B's and an A and another B? Then I'm in Q1, I get a B. I'm going to stay in Q1 with my B. Doesn't matter how many B's I get, as long as I don't get more than 3 A's. Again, if I'm in Q2, doesn't matter. If I'm in Q3, doesn't matter. But if I do happen to get 4 A's, I'm no longer accepting. So if I am in Q4 and I get another B, then that B will not help me. So this is an example of a DFA. This is an example of a DFA that on the alphabet AB that describes the language, all strings with no more than 3 A's. It is an acceptor. It has actually 4 accepting states. It has 5 internal states. We have a transition for, it is deterministic because in a deterministic or DFA, you need to define a transition for everything. So for every A, for every B, we have defined what happens. So we have a transition function for every A and every B from every state. Let's do another example. Here's a DFA on the same alphabet AB, and this is going to be all strings that start with the prefix AB. So what does that mean? Here's what the DFA looks like, but let's build it. So we need to start with the prefix AB. So we're going to start with our initial state. Our initial state is not going to be accepting because if the empty string does not start with an AB, you must have at least an A and at least a B in order to be accepted. So I start out with when I build my DFA, by making a DFA that leads to an accepting state. And then I have to add all of the transitions after that for every possible A and B from each state. And I may need to add additional states, I don't know. So I start out in Q0 with an A, goes to Q1, then from Q1 with a B, goes to Q2, and that is accepting. Now what if I'm in Q2 and I get an A or a B? If I'm in Q2 and I get an A or a B, it's still going to be accepting. It doesn't matter what order the A's and the B's are in, as long as it starts out with an A, followed by a B, any order of A's and B's, it's going to land in an accepting state. Now what if I go back to Q0 and I get a B? Well, if my string begins with a B, it's going to go to a trap state because the rule for this language is that it must begin with an AB. So if it begins with a B, it's going to go to a trap state. So that transition would be from Q0 with a B, it's going to go to Q3. Now what if I'm in Q1, what if I get an A and then I get another A? Well, it can't start out with AA. It has to start out with AB. So if I make it from Q0 to Q1 with an A, but then I'm in Q1 and I get another A, that means my string will begin with AA. So that also will lead to the trap state. If I'm in the trap state and I get an A or a B, that it's going to stay in the trap state is not going to be a part of this language because it did not start with A or B. So that is the complete DFA. All transitions are defined for each state and for each letter for each symbol of the alphabet. All right, let's do one more DFA example. This is any number of A's followed by one B. But keep in mind that the letter B is in this language because I could have, N could be 0. So that could mean that I could have no A's. Okay, so does that mean that the empty string would be accepted? Absolutely not, because I have to have at least one B, right? Okay, so if I'm in Q0 and I get an A, I'm going to stay in Q0. It doesn't matter how many A's I get, any number of A's is fine, and eventually I'm going to get a B, and I'm going to end up in an accepting state. So if I'm in Q0 and I get just a B, that's accepting. If I'm in Q0 and I get A's, I'm going to stay there until I eventually get a B, in which case it will become accepting. Now, I have defined my transitions for any A's from Q0 and any B's from Q0. Now, what if I'm in Q1 and I get an A or a B? Well, it has to end with any number of A's and only one single B. So if it goes any number of A's, BB, or any number of A's, BA, then it's going to land in the trap state. So these are the transitions. And then because this is a DFA, I need to define every symbol from every state. So I also have to say what happens if I'm in Q2 and I get an A or a B. So this is the DFA for that example. Moving on. And now here's an example of a proof by construction. Well, all of those that we just did were proofs by construction because we were proving that the language was regular by constructing a DFA that accepts it, but we haven't really talked much about regular languages yet. But here's also an example of a proof by construction that we want to prove that if L is regular, then the complement of L is also regular. All right, so we could construct a DFA in order to prove this. Okay, so now I'm going to do an example of a proof by construction. So we were already doing proofs by construction before. We were proving that a language was regular. So how do you prove that a language is regular in the classification of languages? You prove a language is regular by constructing a DFA that accepts it. And that is the definition of a regular language. So we're gonna spend quite a bit of time on regular languages. But know now that if you have a language on an alphabet, that language, if you can construct a DFA that accepts that language, then that is in the class of regular languages. So now here's another way to do a proof by construction, and that is we want to prove that if a language is regular, then the complement of that language is also regular. So I'm going to show you how we're going to do this proof by construction. So the first thing we're going to say is there exists a DFA that accepts our language. So we have this, oops, I got to get my pen out here. Let's make a DFA here. So we have, this is our initial state, may or may not be accepting. This is just for, to demonstrate this. And then you have all of these transitions that lead to different types of states. And some of them are accepting and some of them are not accepting. And this defines our language. So we have a whole bunch of states that we get to, and some of them are accepting. Those are the ones that have this double circle, and some of them are not accepting. So how do we construct from this for the complement? So the first step is to make all of your accepting states not accepting. So these were accepting states, but now they're not accepting. Then you make all previously not accepting states, which hopefully I'm paying attention here. So before the other three states were accepting, now these states are accepting. So before Q0 was not accepting and these other states were not accepting. So now I have changed it. So the accepting state, before the accepting states that accepted my language were from my language. They are not accepting anymore. So the complement would be that the ones that previously were accepting are now accepting. So therefore, I have now created a DFA that accepts the complement of L, and therefore the complement of L is also a regular language. So there exists MDFA that has a set of states, an alphabet, a set of transition functions, an initial state, and a set of final or accepting states. And the complement, the set of final or accepting states, is the set of states minus the previously accepting states. So hopefully this is clear and you understand that. This is an example of how to do a proof by construction. In the next video, we will talk about NFAs.